Let's take a look at another example here. I'm going to take an organic compound that looks like this. It has got CH3 on a C with another CH3 and an H and a CH2OH. It's a very simple guy. It's got 1, 2, 3 in a main chain. 2, 3, you know, like that. 1, 2, 3. You got the CH3 there and you got an OH. That's it. It's a, if somebody asks you what is the functional group here, you'd say it's a primary alcohol, right? So I've drawn both ways. You can take either or. If you're interested, I can make them into a box also, actually, like that. It's easier to see them like this, I know, but this is what you need to start getting comfortable with. So the products will only do it in skeletal form. Now you might say, what products, Bilal? So here, let's give you some reactions to make, okay? So the first one is pretty easy. So I'll start from the top left. So I say, okay, so what would the product form if I add PCl5? That's one reaction. Let's call it reaction number 1. Then I'll do a different color. I'll say, okay, so what would be the product formed if I add, let's say, red phosphorus and bromine? That's reaction number 2. And then I'll say, okay, I'll give you reaction number 3, but I'll give you the final compound. And the final compound is this. Sorry. Okay. And we'll have to find reaction number 3 reagents. Okay. Then what would happen if I add, let's say, in reaction number 4, add sodium. You know, you've done that reaction, right? And then 5 and 6 are slight variations of the same thing. Okay, 5 and 6. Let's say in 5, I say add acidified KMNO4 and heat under reflux. That's reaction number 5. And reaction number 6, I say take acidified dichromate Cr2O7, but in this case you heat and distill off product immediately, and you're going to make these different compounds. You might say, well, where do I make them? Well, simple, in the box. If I duplicate this, copy, and I'll just make these boxes here. Come on, no. You might say, where'd they go? Okay, so let me just do this. It might seem painful. I want you to be thinking that you are doing this. So you gotta pause and think. You gotta actually make these guys, okay? So, and for 3, you already made this. So I don't need to make it for 3. I've already, let's say I've already made it. So I'm gonna put that in box 3. Okay. That's box 3. And then box 4 and box 5. Equations 5 and 6. These are all 6 things we gotta build. Okay, so build all the products here. Now these are one-step conversions. Now organic synthesis becomes even more deeper. So I'll do another couple of examples where we go deeper into this. We'll do the same guy and make this. But let's see if you guys can make all of these products and figure out what reaction number 3 is. Now reaction number 1 is the easy stuff. So if I take the skeletal, and if that's my starting point, and I will take the skeletal, duplicate that, put that here. Now I'm just duplicating this. These are not the answers. I'm just pasting them here because the answer will be derived from the reactant. This is just reactants. I'm just trying to do this faster. So if I put this with PCl5, all it does is replaces the OH with Cl. And that's a substitution reaction. And you can also see white fumes formed. Red phosphorus and bromine is basically a replacement of the OH with Br. So now instead of Cl, you get, that's how you get Br. Okay, and obviously heat. You don't need to heat with PCl5. Now in reaction number 3, you remove the OH and made a double bond. That's an elimination reaction. So here, the type of reaction is elimination. And how do I carry out elimination of water in an alcohol? Either you can take Al2O3 and heat, or you can take concentrated sulfuric acid and heat. With sodium, that reaction is pretty easy. What does it make? I should actually have done that, duplicated that. For sodium, made a box for sodium. I forgot the box for sodium, but it doesn't really matter. It makes an anion, O minus, and connects that with Na plus. It's a salt. It's an ionic compound. 3 is elimination of water, also known as dehydration. 1 and 2 are substitution reactions. 4 is a redox reaction because hydrogen gas is given off. 5 and 6 are also redox, but 5 and 6 oxidize the alcohol in different ways. KMnO4 heat and reflux will actually convert the alcohol into a carboxylic acid. So this will become a double bond and OH will add on, COOH. But with dichromate and distill of the product, it doesn't make, the primary alcohol doesn't become an acid, it just becomes an aldehyde, like that. Okay, and yeah, I'll just do that again, and that's the aldehyde. Okay, and obviously it's the O, it's C-double-bond-O. Okay, but you guys get the idea. CHO. So if you're wondering what's here versus what's there, in the bottom case it's CH3 twice on a CH, and the CH2OH becomes CHO. Here it's CH3 twice on a CH, which is then bonded to COOH acid. Okay, easy peasy. And oxidation 5 and 6. Remember, primary alcohols can be oxidized both into aldehydes and carboxylic acids. So, and this is an aldehyde functional group, and the above is a carboxylic acid. And these conditions are what you need to know. You need to remember how to go from a primary alcohol to a carboxylic acid, and a primary alcohol to an aldehyde. Yes, this is CH2OH. The branch is not on the carbon with the OH. You see that? All right. Now I'll show you another example. All right. So let's tell you that okay, now I'm going to take another guy. Let's take something like CH3 methyl propene, which is 1 2 3, and this is a double bond right there. Okay, and and what I'm trying to do is basically I'm going to add steam, and it'll give me two products. One will be the major product and one will be the minor product, and yeah. So now this, by the way, where'd you get this reaction from? This was the electrophilic addition reaction of water or on alkenes. Now you might say, why are we doing this after we're doing alcohols? Because alkenes will make alcohols, major and minor product. And then what in both cases, what we're going to do is we're going to reflux them with, so now I'm going to reflux them with acidified dichromate. Reflux with acid, both products, and let's call them molecules P, Q, and then P will make R, okay, and Q will make S. After, so now we want to make P, S and T. Let's just do that. Okay, P makes S and Q makes T. So the idea is that taking an alkene, adding steam, and what else would I need to add steam? I would need dilute H3PO4 catalyst, and I would need heat and high pressure. I would make two products. You've got to choose the major and the minor. And the major and the minor will come from the one that has the more stable intermediate carbocation. And you have to figure out which two carbocations will it make. When steam is H2O, so if H adds on here, this will become a tertiary carbocation. But if H adds on there, it'll become a primary carbocation. So you'll have two carbocations, primary and tertiary. And which is more stable? So to make this, just to think about this in a second, what I'll do is I'll just duplicate that. So the first part of the reaction, by the way, is the double bond breaks, right? And now the H can come here and a plus charge there. That's a tertiary carbocation. Or the other option is H can go there and that becomes a primary carbocation. So these are the only two carbocations that are possible. So I'll duplicate them so you have both in front of you. Okay. This is the carbocations that are made after adding the water, the first part of the reaction. So it's there and here. This one is a tertiary carbocation, this one is a primary carbocation. Which is more stable, primary or tertiary? Because whichever carbocation is more stable, that'll be the lower activation energy, and that'll be the major product. So the major product will be via lower activation energy, remember that, and minor will be via higher activation energy. And the lower activation energy is one which is the, you can say, more stable intermediate. You got to remember that, because they will ask you that also. Explain why what you have made is the major product, and explain what you made is the minor product. So the minor product has a higher activation energy. That means it forms the less stable intermediate. And now you know you're going to have primary and tertiary intermediates. And which of these is more stable? So the tertiary is the more stable one. So meaning that's where the OH comes into play. So I'll duplicate this, bring it here, make it a little smaller so I can fit in here. Only because I'm using the structural, not the skeletal. You can also make the skeletal. And so the major will get, I'll use green now, we'll put the H there and the OH, because that came from tertiary. And the minor will have the H there, and I'll be primary carbocation. Hence the primary carbocation will make a primary alcohol, the tertiary carbocation will make a tertiary alcohol. Now for both of these, I heat them under reflux with dichromate. What are the two products formed? S and T. Can you guys think of them? Now the only thing matters is what the functional groups are on P and Q. P is a tertiary alcohol, Q is a primary alcohol. So what will these two make? Now if it was acidified dichromate and heat and distill off the product, the primary would have made an aldehyde, but this is unheating under reflux, so it goes to complete oxidation. And when it goes to complete oxidation, then you don't stop at the aldehyde because you're heating under reflux. So what will happen is this carbon that's a primary alcohol will become a carboxylic acid, not an aldehyde. So now it becomes a carboxylic acid. That's the primary. And tertiary, there is no reaction here. S is nothing. S is the same thing as P, because why? Tertiary alcohols do not undergo oxidation. You should be able to remember that. Primary become acids. If this was secondary, it would have become a ketone, but it's tertiary, nothing. Okay. Yep. Okay, so these examples will start getting more and more complicated, because this is how we will learn the reactions.